Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my great pleasure to introduce Wenjun Hu to come to Microsoft and give a talk on mining capacities from concurrent wireless transmissions. Wenjun get her bachelor and PhD degree both from University of Cambridge in London. During her PhD period, she worked on to improve the capacity for wireless networks. And now she's a postdoc at the University of Washington working on improving performance for 802.11 network. Without further ado, let's hear what Wenjun has to say about this topic.
Thank you for the introduction. So I'm going to tell you a little about some techniques we've been trying to adopt to increase capacity. And both of these involve concurrent transmissions, as you will see in a minute. So the world we live in are getting more and more wireless. I'm sure every one of you actually use a lot of wireless devices all the time. Time and time again, you see a cycle of growth. So it starts with advances in wireless technologies, which encourages more devices, more adapters, which actually drives the demand to stress test network, which then say, oh, actually we need more wireless capacities to accommodate all these requests. So for example, if you look at how Wi-Fi evolved over the last 10 or actually 12 years, when it first started, the maximum bit rate was only 2 megabits per second. It's pretty small. It's pretty low, especially in current day standards. Whereas for 11N, which was finalized last year, the maximum rate actually can go up to about 600 megabits per second. That's actually more than 2 orders of magnitude improvements over the 12 years. It's actually pretty impressive. And there's also more interest underway to standardize in the context of 11AC group, trying to achieve gigabits per second. That's almost approaching wireless speed. So let me give you some examples for why we still want to be getting more capacity, especially network capacity. So the highest rates I mentioned earlier are actually raw physical layer rates. So in practice, you don't get the same data rates for transmissions and real traffic. The other part is these rates are actually for the good links. If you have pretty bad channel, the lower end is still pretty low. And in some sense, it's about trying to move up the lowest floor. On the other side, as I said earlier, when you have more capacity, you can actually enable a lot more applications. Some applications that we may not even be imagining at the moment. You look around and you still see lots of wires around. So why shouldn't they be wireless, right? And even more extreme, if we have enough capacity all around the world, then perhaps, for example, we can have a single access point to serve the whole building. And you can do away with all these management issues, trying to set different APs on different floors, making sure everyone gets the right amount of bandwidth and all that. Okay, so we want more capacity. Now, as I said, I'm interested in more network capacity. By that, I mean there are actually two components. One is we want very good link capacity, and also somewhat very efficient media access. So traditionally, information theorists have looked a lot at per link capacity. So the idea is that you want to have very fast links. So typically, you either try to do more tricks over the frequency, more tricks over the spatial domain. General hope is that you want to make sure your transmission is very efficient by using very efficient modulation encoding. And then you can let the Mac to deal with the media access, and hopefully the overall rate will be fine. Alternative view is that, well, we want to have more transmission per time slot. So one way to do that is actually trying to make sure the contention domain is smaller so that we don't have the different transmissions happening at the same time, don't actually interfere with each other. So this is actually not directly media access per se, but the effect is actually media access can be more efficient. So essentially, it's trying to reduce contention domain to make sure that there's more concurrency going on for the whole network. Now, you'll notice that these are actually two classes of techniques, and they address one issue at a time, so either to optimize link capacity or media access, in the hope that overall, when you put this together, you actually have very good network capacity. Now, so how about we try to do concurrency within the same contention domain? What I mean is, ideally, we want to have multiple unipulse messages packed into one, right? And have this broadcast to all the interested parties, even if they only want one of those messages. Now, the hope is that by doing this, you're able to kind of jointly optimize both the per link capacity and also the media access, right? So now this is actually not very easy for good reasons. So there are basically two questions. One is, how do you do the coding, sort of coding operation? So how do you pack up all these individual messages into one broadcast message? And on the reverse side, how to retrieve the individual messages from the broadcast packet. Because whatever message you don't want is actually interference. And the reason we didn't want to do concurrent transmission in the first place is because we don't want the interference, right? And there's also a more kind of system side, in the sense that how do you know where there are these so-called coding opportunities? Or in some sense, I've listed decoding because in my experience, really, a lot of it is about figuring out how to decode, and then the coding comes up very naturally. Now, I've actually listed only two examples for how to identify it, because basically it's a matter of how do you figure out which packets to pack up together, because they don't always work just naturally. And another more system level question is, when there's dynamic traffic, how do you figure out when to do the right thing at the right time, making sure that all your objectives are kind of achieved? Now, if we look around all the techniques and all the prior work in literature, there are actually some ideas from information theory which roughly addresses the first part, like basically the kind of encoding, decoding operations. But for the second part, it's actually much less clear. There are certain suggestions perhaps, but they may not necessarily translate into practice. So during my thesis and postdoc work, I basically work on these two topics I listed earlier. One is called network coding, and the other is multi-user MIMO. For both of these, they're actually the primary goal. When the techniques were first proposed, they were intended to increase network capacity. But of course, as time goes on, people realize that you can actually adapt these to achieve different goals, like increasing reliability or fairness or whatever, which I would generally call secondary goals. Now, in this talk, I'm going to focus on the first part, like the left-hand side, introducing two protocols called COOP and COOP. They're both trying to achieve capacity. I will try to address both of the two challenges I mentioned earlier, but with different focuses. I will briefly explain network coding in hoping that you will understand how we can identify the coding opportunities. And then I'll explain in more detail how the coding operations work in the context of multi-user MIMO. So there are actually two themes for the whole talk and for my work in general. One is trying to turn theory into practice. By that, I don't just mean implementing an algorithm and study the performance. The techniques I mentioned are actually general classes of techniques. The specific algorithms actually differ in different scenarios. So in this case, in this context, for our work, the COOP was the first time the network coding was actually properly integrated into the stack as a protocol, and we studied performance and interaction between different layers. COOP is the first algorithm trying to achieve this kind of scenario without using actual resources on transmitters. I will actually explain later on what this means. And what's interesting was that through both work, we actually realized that both achieve a large set of gains. These are actually not obvious from theory. I'm not saying theory is wrong, but because of different focus or different way to look at it, some issues may not show up in theory. The second theme, it's more of an observation rather than a goal or anything, is that although these are actually very different techniques, or they seem to be from different backgrounds, in my view, they're actually all about different ways of addressing the interference within concurrent transmission. So in the case of network coding, it's about trying to use side information from the extra hop. In the case of multi-user MIMO, it's trying to use the information from the extra antenna. And then these are both the operation side, the coding operation side, and in terms of system level identifying opportunities, they actually share very similar concerns. Okay, let's get started. So network coding generally means that a router in the network is allowed to mix packets rather than just forward packets as they are. So until we did this work, there was lots of interest in theory. It came out from multicast in wide networks because there are lots of actual packets sort of along the side which you can make use of in decoding. Whereas in comparison, as I said earlier, we turned that into a protocol and then integrate that into network stack for the first time, which addresses a lot of protocol issues. And then in theory, typically, you need to know everything about the network. By that, I mean you need to know senders, receivers, you need to know the flow situation along the whole topology, the rates, the capacities on each link, the rates you want to achieve, and all of that. And then typically you run global optimization, and then it's very natural how you should do code, how you should do coding, how you should do decoding, and where they should happen. Whereas in practice, what's more common is that you have to make use of local information and then try to do all the operations in a distributed way. Okay? I'll explain what we mean by that. And the other thing is, typically when you do these optimizations, sometimes it's actually implicit that you will need to delay packets to wait for the coding option to arise, because you know that at some point some packet is going to come along from different paths, and then your packet needs to be there to be able to do this coding in order to achieve the capacity gain. Whereas when we do it opportunistically, in the sense that if there are opportunities, do it. If there aren't, don't wait. So in some sense, this is more about improving throughput rather than capacity per se. And finally, typically theory was only talk about the network coding layer, so to speak, whereas we actually saw a lot of cross-layer effects, and which give you many more interesting insights into what happens when something like this is implemented into network. Okay, so let me give you a simple example. This is actually taking a leaf out of Yunnan and Phil's work, although neither of them is here right now. So Alex and Bob wants to exchange information via the access point. So conventionally, that's what you do. Alex sends a packet to the access point, Bob sends it to as well, and then the access point forwards on individually. So altogether, this scenario requires 4 transmissions. Okay? Now instead, what we could do is the same as before for the first hop. And then this time, instead of sending them individually, you put them together through bitwise XOR to combine these 2 packets into one, and then broadcast. So when Alex gets it, it has her own urgent packets anyway. So she does another XOR operation for these 2 packets and retrieve Bob's packets, and similar for Bob. Now this is simple, but then what it does is that we can actually use only 3 transmissions for the whole scenario rather than 4. So you kind of expect about a 30 improvement throughput. So just to recap the whole scenario again, the access point, or in really more generally, this is the relay, does the encoding. It tries to look for the right packet to code together, mixes them, and then adds some method information in the header between the MAC and IP, and sends it in broadcast mode. And for Alex and Bob, they first of all have to keep copies of the packet they sent out in the first place. And then when they receive a packet, they detect that there's an extra header there, which indicates this needs to be decoded. And then they retrieve the right packet based on that information, do another XOR. And you will notice that by doing this, we only require distributed local action. So this is how we achieve distributed protocol. Just to highlight a few points, the XORs on both sides are the coding operations I mentioned earlier. For Alex and Bob, the fact that they have sent packets are the opportunities, in fact, for decoding, or sometimes we call that side information. The packets in queue is basically saying if there's congestion, then you want to worry about coding. Otherwise, there's really no need because there's already enough capacity. This makes sure that you don't actually delay packets unnecessarily in order to wait for coding to happen. Then finally, the fact that the access point can look at the packets in the queue, and then realize that they actually went through different path segments, the same path segments in different order, means that they actually will be able to decode. So with this confidence, the access point does the coding, and in the hope that it's going to work out. Okay? So we implement this scenario in Click and RoofNet framework. We want to compare the coding and no coding scenario I just explained. We send UDP traffic between Alex and Bob, and then look at what different link quality between the access point to Alex and Bob hop. Okay. Now this is what we see. These are results from the testbed. We compute the ratio. The y-axis shows the ratio of the throughput when you end-to-end throughput, when you're doing coding versus no coding, whereas the x-axis shows the different bit rates for 11B. Notice that I've drawn a line here, which shows roughly this is what we expect from the early analysis. Now, what you see is that actually, in practice, we get a lot higher benefit. For almost all of them, the throughput almost doubles. Okay, so this is pretty good. I hope you agree. Why is that? Now, we realize that in this case, we actually need to look at what happens at the media access level. The MAC tries to be fair, so it tries to give all of the parties here, Alex, Bob, and the access point, a third of slots each to send the transmissions. Now, the problem then is when there's no coding, because the access point needs to send twice as many packets as either Alex or Bob, it actually needs twice as many slots. So there's actually a mismatch between what it gets and what it needs to send packets. Whereas when there is coding, all nodes actually need to send the same number of packets, so the mismatch goes away. Okay? So, okay, the Alex-Bob scenario is actually very simple and somewhat limited. So one way to extend that is to say, now in this case, instead of having the packets originating from Alex-Bob just sort of swoop around, you can have them having Eve sending packets through the access point to Bob, and Fred having packets for Alex through the access point again. And you notice that in this case, when Eve sends the first hop packet, the Alex can actually overhear it. And similarly for Bob, it can overhear first packet. So which that means by this point, it actually looks the same as the scenario earlier, that the access point can actually just do XOR again of these two packets, and then the Alex and Bob will have another packet for decoding, and you can repeat the same scenario. So basically, by using overhearing, we're able to make use of send more packets together, get higher throughput. This is more details actually in all these papers I mentioned, and I won't go through in more detail. Now, another way to look at this is, what if we only do one-hop scenarios? Because earlier, the scenarios I showed you all require some kind of mesh traffic, and especially you actually need kind of traffic to cross to create these kind of opportunities. This is fine if it happens. Now, in practice, there's also a large number of tree-like kind of traffic. So think about what happens when you download stuff from the internet. Typically, you get all the traffic coming down from access point. So one hop is actually going to be very useful if we can do it. So this brings me to the next part, which is multi-user MIMO.
For the first part, I record this basically tree distribution is what mentioned during the COOP talk. Basically, people observe.
COOP?
Yeah. Basically the original network coding when using wireless mesh network. Because in practical network, you don't have as much cross traffic.
Right.
As basically this improvement.
Yeah.
Did you later do basically practical deployment study and these kind of things?
No. So I have two answers to that. One is part of this will actually be addressed in the second half of the talk, but that's going to be using a different scenario. The other is for network coding, part of the assumption is actually that you have a very kind of mesh scenario. Mesh not necessarily in the way people look at mesh people have different notions of mesh networks really. So what it's most appropriate for is if you have some kind of local network where people need to talk to each other anyway. So more naturally you get this kind of cross traffic. Now that's for COOP as it is. Another way, so like Sachin, for example, did a bunch more work trying to bring the bit level operation to the symbol level, which then means there's actually a lot more opportunity to do a bit more tree-like. Okay. In that case, it's still not the more general tree-like, but for example, if you traverse a linear multiple hop, and then you can potentially try to use symbol information to decode at a symbol level. Okay. So it's done slightly, but not more generally. I think there's actually a lot of interest in trying to address that scenario. I don't know about all the work. I know there's some in theory. I don't know about any more practical work, because part of it is also what we can evaluate right now has to be based on the current scenario. But it's hard to say how it's going to grow in future, and then there's a bit of chicken and egg problem in that sense. did that answer your question? Not very much, but
some of the questions. Maybe we can hear the second part of the talk, and then I still
Right.
going to basically
Sure,
ask some.
sure. We can discuss that again. So for the second part, I have to start with some background first. But let me just tell you what this means. So let's go back to the Alex and Bob scenario. Now you will notice that this time they have multiple antennas. And let me actually mention that these are multiple active antennas in the sense that the antennas will be used at the same time. This is different from the typical access point you see even nowadays with two antennas, but they only use one at a time. And now we're only interested in the second hub. Sorry, so they have different antennas, and we kind of pretend that even though these antennas are on different devices, they could be used altogether as if they were on the same device. This is what we mean by kind of multi-user scenario. And the other thing is, I should mention that at the moment I'm only addressing the hub from the access point to Alex and Bob, so it's like the second hub of the earlier scenario. So this is kind of the tree-like kind of traffic. And this is usually referred to as downlink. Basically, there's one transmitter and multiple receivers. So again, here's just a summary of what's being done in multi-user in theory and what's in practice. Now, you'll notice that there are actually lots of terminologies. So I will actually come back to this slide later on after I've explained all of the things. But this is just to show you that we've done a bunch of stuff to address various issues in theory, and we found interesting things in practice. Okay, and also, I just want to remind you again the challenges I mentioned earlier, that there are two components, both the coding operations and the identifying coding opportunity. Now, I've organized them slightly differently in the sense that this time, the coding operations basically happen at the physical layer for symbol level operations, whereas the finding coding opportunity is more kind of macro layer and above system level kind of issues. And I'll just say that this part, the lower part, is actually very similar to what we saw earlier. So in some sense, you can pretty much just copy over directly, maybe just moving it to a lower layer. And for that, I'm not going to mention anymore. And then I'm going to discuss a little more how the coding and decoding operations work for this scenario. And we need to go back to some background to start with. So a MIMO channel really is a set of channels. So you will see that on each side, the transmitters and the transmitter and the receiver both have multiple antennas, and each of these transmit and receive antenna pair actually has a pause in between them. Typically, if the environment has a kind of multi-pause fading property, then all of these paths will have different properties when the signal goes through them. So typically, these H's will actually describe the phase and amplitude attenuation, the amplitude attenuation and the phase shift as the signal goes through this path. And quite often, they are represented in a matrix format so that they can be used, mathematical operations for matrices can be used to analyze these kind of scenarios. The main general thing is all these H's should vary independently so that we can make use of the nice matrix properties. Generally, they will mean that such a matrix is actually spatially uncorrelated. And then this will generally be called the channel state information matrix. Okay? I'll try to avoid using terminologies, but sometimes I still need to introduce them. Now, the basic way to make use of MIMO to get good throughput is to actually send as if one packet on each of the antennas. These are usually called independent streams. So basically what happens then is you send one out of each transmit antenna, and then they go through the network along different paths. And then on the receiving end, each of the receiver antennas will actually tend to measure a linear combination of the packets. So you might notice that these H's are the same coefficients I mentioned earlier on different paths. And these are the two packets. Now, typically, by linear combination, what this means is that each of these received signal components will actually have interference from the other packets. So, but then you might notice this is very similar to simultaneous linear equations. So we have two unknowns and two equations, so that's fine. The receiver solves the equation, recovers the original packets. Okay, so this is already available in commercial chips. So this is actually practical. It's actually really feasible. I've simplified a lot of issues there, but I'm happy to discuss afterwards if you still have doubts. Now, this is good. There's just one point I want to mention first. The fact that we actually have to cancel out the interstream cancellation means that you tend to lose capacity when you do it this way. Okay? with two exceptions. One is if the channel matrix have a special orientation. I'll explain that in a minute. Or another way is the channel matrix is orthogonal. This is very rare in practice. Basically, I have yet to see a matrix that really does that. Okay. So alternatively, so we have the same packets again, right? Now, instead of sending them one out of each antenna as before, we try to send out some linear combinations. So these V coefficients come from a different matrix, basically, okay? Such that when they get to the receiver, there's still going to be some linear combinations. But then when you solve the equation and then recover them, you will actually not lose any signal power from doing the cancellation. So I know this is a bit vague. If you are actually familiar with matrices, this is based on the singular value decomposition of the matrix. I'm not going to explain that in more detail, but what I was just mentioning is that so first of all, I will usually refer to this as an SVD-based precoding for later purposes. And then here are just a few general facts about these kind of operations, so that even if you don't understand anything about the basic math, here are some high-level conclusions I want you to realize, and this will help you to understand the scheme later on. So basically, these are the two techniques I've told you are basic single-user MIMO techniques. The first one is very simple, but it's actually suboptimal in most cases. So basically, in performance terms, this is some kind of average case. Okay. The upside is just the transmitter doesn't need to know anything about the channel. You can just do it, and you'll get something out of the channel. Alternatively, if you want to get the best out of the channel, you need to know very accurate channel information. And then doing the SVD precoding can give you the best results. With one catch, typically, the streams you get out of that tend to be very uneven, in the sense that the best will be better, the worst will be worse compared to not doing encoding. Just to give you some idea what I mean by these very uneven streams. So in this case, I've looked at out of 2x2 matrices. There are two streams out of these 2x2 matrices. Then I try to compute the ratio between different streams using different techniques. I'm not going to read these numbers, just to give you some sense of how the statistics might look like. And then for the third point, I'm trying to show you the comparison between the best stream from SVD precoding and the basic multiplexing. Okay. Now, it may be hard to see what those numbers mean. Just to give you some idea, when you have a ratio of 2, it basically means if it's translated into 11n terms, it can step up a rate by 6.5 megabits per second. This is out of 65 megabits per second total possible. So this is actually 10% improvement, which is pretty significant. Whereas if you have ratio of 10, it basically means the stronger stream can potentially be can use more than twice the rate or even higher, depending on your starting point. So basically, even a slight change in the ratio can actually mean a lot of performance difference in practical terms. Okay? So this brings me back to the scheme I'm going to talk about. I hope that was clear earlier. If you have questions, I can explain later on. Now, we have the same setup again. One packet there are two packets. And then we do the same precoding as before. You might notice this is the same V as I was showing you earlier. Now, instead, this time we actually send these two packets to two different people. Okay? And on the receiving side, basically each of these antennas will see a linear combination of the two packets we saw earlier. Now again, notice that every one of them actually has two unknowns and two equations. So they could actually solve the equations on their own, right? And then recover the original packets. Now you might notice, I'm not sure it's very clear. So there are the two middle packets actually seem to be fainter than the other two. I'm trying to indicate here that most likely they're going to be weaker and with errors. But then that doesn't matter because we don't need them anyway. The Alex and Bob only wants the packets that was intended for them in the first place. Okay? So just to recap what I just showed you, you start as if doing SVD precoding for Alex, right? So you will get a strong stream and a weak stream, right? Now, instead of sending the weak stream to Alex as well, you try to replace it with a stronger stream for Bob. Hope that altogether, by summing this up, you actually get better across both. Okay? And the general thing is that the precoding should actually achieve these kind of effects. So the key here is really about how to do precoding properly. So for precoding, once you have the channel from both Alex and Bob, so if it's a narrowband, by which I mean the channel details can be described by a single channel matrix, okay? And this is a scenario I explained all the way through up to this point. So in this case, basically what you do is you find the SVD precoding matrices for Alex and Bob respectively, and then try to see which one would be better for both of them in the scenario I just explained, okay? And the second part is the only extra step really to what's required for SVD precoding earlier. Other than the discarding, but that's pretty straightforward. Now, if you have a wideband, by which you can just think of this as the channel detail can be captured by many parallel, not necessarily parallel, many narrowbands, many matrices. So if you are familiar with OFDM, that will be one example. So what you can do then is you do the same as for narrowband, and then you can fine tune on each of narrowband. So for example, if you have OFDM subcarriers, you can do the same thing for each different subcarrier and then try to hope that it's going to be better overall. Okay? So why do you expect benefit from this? Now, let me first remind you again, I told you earlier about two single-user multiplexing techniques. One is the best case, one is the average case. So when you use COOP and using Alex precoding matrices, basically for Alex, it's going to be like the best case for her for the strongest stream. Okay? Now, in the average case, for Bob, his stream will be like as if he's getting from basic multiplexing, so that's going to be an average case, right? And in some cases, you can actually have matrices so arranged that you will be able to get both the strongest stream out of both of them. Now, of course, there's a worst case that I didn't list because it could happen that Bob will basically get nothing out of the channel, but that's actually very rare, sufficient that it's usually not going to be of concern anyway. Okay? So let's try to evaluate it just to see how well it does work. We have a lot of channel matrices measured, or the channel information measured from our stationary 11 testbed. These have MIMO antennas and basically give you a lot of very detailed channel matrices for different bands. And they are OFDM, so basically it's kind of a wideband scenario. And then the data is such that we can get a channel sample roughly about every 6 milliseconds, so it's pretty detailed. And the other key data we have, it's not actually directly measured per se, but basically we have some mapping of SNR, the signal to noise ratio across wideband, and the rate mapping. This is actually from a separate work where I can explain offline if you're interested. Basically, given some rates, given some SNR, we can be pretty confident what rate will be supported on that kind of channel. So with this, here's just a picture showing you one of the testbeds. The blue dots are just where the nodes are. These are the antenna setup, and the picture over there is the actual chipset we're using. Okay, just nothing fancy. It's a very fairly dense cubic environment, and then so we get a lot of multi-stream kind of scenario. Now, before I go into further detail, let me briefly comment on the channel variation. Even though it is a very stationary testbed, and we try to collect data overnight, so there's pretty much as little variation as you can imagine, we actually still see a fair amount of variation. This can be, there are environmental issues, there are measurement noise, resolution. Basically, we can't control any of these. Now, the main point here is these are actually pretty unpredictable. So it's very difficult to estimate what's going to happen, to guess what's going to happen and try to optimize for that. The effect is that when you do any kind of precoding which requires channel information, if there's any delay, you actually lose a lot of performance benefit from trying to do very fancy optimizations. Whereas across different delay periods, partly because these are still stationary, you actually don't see very much difference. So I'm not going to bother specifying how much delay there is in the results later on. And the other thing is, all this kind of channel variation basically means that when you want to do very complex precoding, you may actually not get what you wanted to get in the first place. So the way we do it simply actually may be good enough. Okay, so we want to compare the capacity, which is like the I would go to start with. So in this case, there are two ways to look at this. Either Alex Bob trying to do the per link, take turns trying to access the link, and then in either case they can use either the SVD SVD precoded multiplexing or the basic multiplexing. Okay, and then we can sum up the rates across both slots and try to average up to see how much they get. Alternatively, they can access both slots at the same time using COOP, I just mentioned. Okay, and then we want to compare the sum rates in all these three scenarios using basic multiplexing as baseline. Okay. Oh, sorry, I forgot to show you this. That's basically the two scenarios. Okay. So in this graph, I'm trying to show the ratio of COOP over the basic multiplexing and SVD precoding over multiplexing in the scenario I just showed. The y-axis shows you the CDF over all the unsaturated links. So because some of the links actually can support more rates, higher rates if they were available. So I've taken these out just so they're not skewing the results. And on the x-axis, you see the ratio of all these. So there are two lines. The red line shows the gain of COOP over the basic multiplexing, and the blue line shows SVD over basic. Okay. Now you see that for SVD precoding over basic, median gain is about 19%. It's modest, but it's okay. Whereas in comparison for COOP, we get about twice as much gain in terms of absolute improvement. But the other interesting part is, if you look at the high end of the curve, actually, for some of the link pairs, you get a huge amount of benefit by doing either, but even more so by doing COOP. Okay, so even if you compare so actually, I don't know if you can see the blue line stops at about 2.5, whereas the red line stops about 3.5. So even in that case, COOP still gives you about 40% improvement over the blue line, the SVD precoding. Okay. Okay, so we seem to be happy with some rates, but let's make sure that everyone is happy as well. So in this case, we want to focus more on Alex. Now, Alex either takes turns to access the channel using the two basic techniques again, or tries to share the channel with Bob using COOP. And then we want to compare what Alex gets per slot using either of these scenarios. So again, I'm showing you the ratio of these rates on the x-axis and the CDF of all the same links. Actually, all the links, non-link pairs, because these links represent represent the x point to x hop. Okay. Now, there are three lines. The blue line is again the SVD over basic. The red line shows you what happens if Alex finds the best partner link to share the channel with, and the green line it shows you what happens when Alex finds the worst possible. Okay. Now, what you see is, if she has the right link to share the channel with, then the median gain is actually about 67% improvement. Okay. Whereas even the minimum is about 18%. So this actually means almost everyone gets some benefit, modest or lots, depending on the channel. Whereas in comparison, even the median gain for SVD-based precoding is about the same. It's actually, so I've only shown 2 decimal points, so the median gain for SVD is slightly higher, but basically they're about the same. Okay? And the other interesting point is that if you look at the worst part for this part I've circled out, even for the worst links, even for the worst partner links you can have, for some of the links, you actually still get a lot more benefit than doing SVD precoding. Okay? Right, so let me briefly comment on the complexity about the scheme. I've been trying to say it's a very simple precoding technique. By that, I mean the basic that's required for doing SVD precoding is actually already supported by hardware. You don't see them available right now in commercial products, but there are already these components there. They just don't support a full kind of protocol exchange. And what we need on top of that is basically very modest. And then the graph earlier hopefully will convince you that in many cases, actually even a random partner link will actually be good enough. This means you don't actually need to worry about a lot of scheduling issues or trying to figure out what's the best about, and depending on what the traffic looks like, it may become some complexity. Now, the third point is that typically when you have all these different different streams, like I said earlier, because they're so uneven, the best thing to do to make use of all the capacity is to use different rates on all of them, right? Otherwise, you tend to lose a lot of benefit from either the stronger one. But actually, it's not necessary in our case. I'm not going to show you any more results, but basically the gain is actually even better for us in that case. Now, I should mention that none of these actually applies to the existing theoretical analysis. So these are certainly definite contributions from my work. So I showed you this slide earlier. Let me come back to it and explain what's going on. Typically, in theory, the focus is on a scenario where the access point has more antennas than the clients. So what this means is that you actually, either if you want to add more antennas, so this actually incurs higher hardware cost, or the hope is in general that when you have more antennas, you can just support more streams so that you can get higher total altogether. Now, this is fine if it actually does work out like that, but in practice, there are these two issues. One is, given your device size, your separation between antennas may be limited, and that's actually very crucial to getting good performance out of MIMO channels. Second point is that in practice, again, your transmitting power is going to be bounded. So typically, what happens when you have more antennas or more streams is that your per stream power actually gets less. Okay? So with these both issues combined, you don't really get more necessarily higher sum capacity if you have more streams. Now, and it's typical that the precoding operation I keep referring to will be very complex in this kind of scenario. Basically, the simplest will be a lot more complicated than COOP. I'm happy to explain in more detail offline. And the typical assumption that's very natural as well is to assume that the transmitter have full knowledge of the channel behavior. So it's kind of the ground truth behavior of the channel. But in practice, you actually never get that anyway. The other thing is, most of the results we've seen is from narrowband, in the sense that you only have a single matrix capturing the channel. I mean, that's fine because typically it's very hard to know what the channel behaves precisely. The other typical way to do in theoretical analysis is to look at channel capacity. Now, that's all great, except that there are 2 points here. One is the channel capacity is actually continuous capacity. So, and basically means, and also there's no absolute highest cap you can get. What this means is that any gain in receive power will be useful. Although maybe at higher end, you will actually get less bits per hertz, whatever, out of any gain. But you notice that all of these actually don't apply in practice because of various practical conditions and the way we want to do things. So in comparison, what we've done is we've actually shown you a technique for when the AP does not have actual antenna than clients. The precoding I introduced was much simpler, which accommodates for delayed channel knowledge as a transmitter. We've shown you some wideband results, and also the rates are using 11N, mostly because they are discrete and capped. So it takes into account the fact that you don't always make use of any power gain you harvest from the channel. So just to show you one simple scenario, I've basically taken one of the simplest, reasonably simple technique from theory, in the sense of it's being practical, and then trying to compare that to COOP. To COOP. In this case, there are actually 3 antennas on the access point, the same setup for Alex and Bob, and then we again use the sum rates comparison that we did earlier. This time there are 358 link pairs, including some that's very saturated. Okay. Now what you see is that, so again, the red and blue line follow the same convention kind of as earlier. What you see is that the red line, which is COOP over basic multiplexing, is actually almost always better than the blue line. Even though we are not using actual antennas, we are using much simpler precoding. Now, of course, the title is meant to get your attention. I don't mean theory is wrong. But what this actually shows you is that there are lots of operation conditions when theoretical techniques don't actually necessarily give you benefits. Whereas we can, by taking into account the various issues in practice, we actually get a lot more out of something simpler. Okay, so I'm about to conclude. I think I'm fine on time. Now, just to recap, I explained in various detail two practical techniques to achieve concurrent transmissions. And there are really two ways of canceling interference, two ways to cancel interference within the kind of concurrency transmission in the same contention domain. COOP is a practical network coding technique, which is first time it was a protocol integrated into network stack and it was implemented as a full system. The key here is that it uses bits from the extra hop to cancel interference from the concurrent transmission. And COOP is a practical multi-user MIMO technique, which is the first algorithm for a case scenario where there's no actual resource required on the transmitter. And it uses signal from the extra antenna to cancel interference for these concurrent transmissions. And in both cases, you actually see that there's actually a large improvement in terms of throughput or rates by using these techniques, and they're not obvious from theory. So this basically means that doing concurrent transmissions like this can be very useful, and it doesn't need to be complicated or theoretical only, it can be practical. Okay, so just some brief idea for future work. I mean, of course, multi-user MIMO seems there's a lot more to do for multi-user MIMO part. So for example, the precoding decision can be extended to reflect different goals. Like what I sort of focused on earlier basically tries to improve the sum rate, but now you can imagine trying to adapt that for increasing fairness for whatever definition of fairness you want, or maybe more reliability or some other interesting properties for the network. And naturally, there's the uplink side, the hop from X and Bob to access point. I mean, it's not going to be the same, but something interesting can be done. And actually, some work at Microsoft Asia is already looking at that, although they use different antenna settings on different nodes. And the other interesting question is, MIMO is really a spatial domain technology. So can you do something equivalent, or not equivalent, but an analog to that in the frequency domain? And there should be something interesting. And the other thing is, part of the reason these two topics are in the same talk is that there should be some connection between them, right? So for example, in the case of COOP, there are actually some bits that's discarded. Maybe you can make use of that somehow for whatever reason. And the other thing is, like I try to say, in some sense, there's some kind of equivalence when the extra hop gives you information that the extra antenna gives you. So you can imagine that some technique can be devised to combine these two in some way. Just a quick acknowledgement for lots of people involved on these two projects, and that's it.
Thank you very much for the excellent talk.
Thank you.